I'd rather just show you the steps, but I really do want you guys to just practice through this stuff. It's not too hard once you get into the nap, and I'll tell you what all the steps are. And so you want to practice this stuff. I'll kind of fill in the blanks. Next Monday, I'll probably fill in the blanks on an integral as well, and then just hand it off to you. But let me just walk you through these steps. Let's begin. So from last time, we were studying this integral for the posterior predictive distribution. So last time, we had this model set up. So here's our example. We said xi's are coming from a normal distribution. We know sigma squared for some unknown reason. But we don't know mu, and we want to be able to infer it so we can predict the future. I'm going to put a flat prior on mu, standard reference choice. And then I want to find this posterior predictive distribution. So all that is, by definition, is this integral. So this is the posterior distribution. This is the sampling distribution, right here. So I'm just doing a weighted average of the sampling distribution. And so I write this up to proportionality. I get rid of my normalizing constants. I know sigma, so I can just chuck that and not track it. If you felt like keeping track of all of this at the very end, you wouldn't have to work out which normal it is, but you would be expanding squares, completing squares a couple times through the problem. So I usually like to mitigate that just by tossing the normalizing constants and not keeping track of them. And so what I've done here is I factorized out everything from the integrand that doesn't have anything to do with mu. And I compartmentalized everything in terms of the mu squared terms and the -2 linear term. And then I can recognize which normal this is. Now there's a couple different ways you can proceed. You can complete the square right here. And if you know how to do that, what you're essentially going to do, you want to always look over here and make sure whatever's leading the quadratic term, you can factorize out of everything, and then you can complete the square. What I typically do is I recognize which normal this is. And then I write down the normal and I expand the square and I see which other term is left over. And what I do is I add and subtract that term so that I have a perfect square right here. If it were a perfect square, then that would be a normal, and it would integrate to the inverse normalizing constant of everything. And so which normal is this? It's not too hard to recognize. I recognize the inverse variance right here. So this I just plug in 1 over sigma squared plus 1 over sigma squared over n inverse. And then I work out the variance by isolating the -2 linear term and multiplying it by what I just found. And so I would just take this thing right here and multiply it by that, and I'd have the expectation. So let me just write that down over here. This would be x tilde over sigma squared plus x bar over sigma squared over n times that variance I just found. 1 over sigma squared plus 1 over sigma squared divided by n inverse. And I'd plug that in, and I'd figure out what I knew integrated to 1, and everything else left over, would be the answer to my problem. So that's the way I do it. Turns out when you go through that work, this is the answer. So you can see this inverse normalizing constant. So it always looks like, if you want to see what it is, if you figure out what this variance is, this is this in disguise. So it's just rewritten. And it's always the expectation squared is what you end up putting in there. So it's always going to be this expectation term squared times that variance. And so if you don't believe me, go through the exercise and you'll see that. Or you can check back in your high school notes, and that's what completing a square always looks like. And so I have to keep track of this part too. So I keep that right over here. I've been storing too much information. I did factorize all this out, but I could have gotten rid of that. I could have factorized that thing out and just written up to proportionality. So, and I'll get rid of that here as well. So sometimes it's good to just chuck everything as you go. Sometimes I like to write down all the information so that I can backtrack my work and see where it all came from. And so at the end of the day, this is the answer that you come up with. When you work this thing out, you're going to wind up with something proportional to this. And from this, I can work out what the expectation and variance of this distribution is. Keep in mind the random variable here is x tilde, that's our future. So I look for the quadratic term, and I can figure out what my variance is. So, and then I figure out what my expectation is. And it turns out when you do this, so can anybody recognize this? Give me a simpler expression for that. Invert that thing, right? And so I'm going to write down 1 over sigma squared minus 1 over n plus 1 sigma squared invert. And that's a pretty ugly way to write that. What's that? It's not quite.
N over n plus 1 sigma squared.
There you go. So this shouldn't have surprised you. Sigma squared times 1 plus 1 over n is one way to write it. And so I like it that way. That's what we figured out last time. And so when I take this thing and I multiply it by this, what do you think you get? So keep in mind, n over n plus 1 is just that thing right here. So I could rewrite that the same way. What do you think this answer is? N x bar, so here's the expectation. Be real specific, x tilde given x. This will be equal to n x bar over 1 plus n over sigma squared. These are squares right here. Times sigma squared, 1 plus 1 over n. Pretty funky way to write this down. Let's reduce this to x bar. If you go through and simplify it all. And so it's just an exercise in keeping track of everything, and it's a lot of algebra. And so I gave you a tool last time so that you could have recognized probably at this step, as soon as you expanded the square, you knew that this was going to be something to do with the inverse normalizing constant of a normal. And this thing is a e to the minus quadratic form in x tilde. At this step, I already know this thing is normal, because I've got e to the minus quadratic form. And I know about the forms that this thing integrates to. It integrates to this stuff. It looks like another exponential. So it's going to be e to the minus quadratic form. That has to be a normal. And at that point, I would probably stop and I would do the iterated expectation and variance. And you would have come up with these exact same answers. So multiple ways to do this problem. One is fast, and one is the way that you can always use if you get confused, so long as you know how to integrate.
So I have two questions. First, is this exponential plus half?
Yeah, it's plus, because it's the inverse normalizing constant. You'll notice that there's a sigma up here, and the 2 pi is up here. So what was this thing that we integrated? It was the inverse normalizing constant.
Oh,
So this was the completion of the square term that I had to subtract off.
okay.
And so when it got
Okay.
flipped around, it's a plus sign. Yeah,
And here it's not enough for.
that's why I wrote the plus sign so clearly.
It's not enough to know that the first term is the kernel of a normal, because we still have the other exponential term that we need to multiply in.
Once you do this exercise once, you'll notice that that's also e to the something. It turns out it's just a linear in x tilde, or it turns out it's quadratic in x tilde. So this still looks like a normalized normal. So multiplying these two things together still preserves that form. So is it enough to just say, I mean, for me, sometimes I say it's enough to just do this and I know. So is it enough to just say, I think if you know, then yes. If you're trying to demonstrate to somebody what happens, then maybe it's not enough. If you're taking an exam, maybe you want to carry it through all the way. Make sure I understand you know the steps. Any questions about all this? So this is the hard way to do the problem. And if I were to actually do this on the board, I would have quite a few more lines right here, not just simplifying everything as I went through. Probably would have taken me a little bit of work to go from here to here. So, but it is just completion of the square term. We'll be doing this whole example again, but with Poisson. But before we do that, I want to show you an algorithm. And I use this algorithm quite frequently. this is the Monte Carlo procedure. For posterior sampling. Now you might say, why do I need a Monte Carlo algorithm? You might not even know what it is quite yet, when I can just work out this integral. The whole point is sometimes this integral can be intractable. You won't be able to write it down analytically. I wouldn't do Monte Carlo if I knew my posterior predictive was a normal x bar sigma squared times 1 plus 1 over n. I know what that is. I know all the properties of that distribution. If you wanted intervals, I would just give them to you. If you wanted the mean of that distribution, I'd add you x bar. If you wanted the variance, I could pluck it off. Any description you wanted from that distribution, I could tell you about because I'm so well acquainted with normals. But you could imagine that we don't know what this integral is in some cases. And you might want a computational tool. This computational tool is pretty cool. And so it consists of 2 steps. So, 2 sampling steps. Before I continue, please tell me what Monte Carlo is.
Average.
It's averaging. So averaging is averaging. So you might average in your Monte Carlos, but I don't know if that's the full description of Monte Carlo. It's Monte Carlo. It's an algorithmic class. It's a whole suite of algorithms. Annie?
It's when you come up with something that you know the answer to and you kind of test it to see if the answer you calculate matches the known answer.
That's what you do on your homework. So you use it as a tool to do that, but I don't know if that's a description of Monte Carlo, but that's how you've been using it on your homework. And so you kind of know what the answers are, and then you simulate to see if it all works out. So we use this tool all the time. A lot of times we use it when we don't know what the answers are, and this is our answer. So Monte Carlo is an algorithmic class that gives you a random answer in a fixed amount of time. That's a property of these algorithms. The answers converge to the truth if you let that time extend into infinity. And so Monte Carlo is an algorithmic class, algorithm that gives a random answer in a fixed amount of time. Of course, we don't want just random answers. We want answers that are randomly floating around the truth. So for your Monte Carlo algorithm to be good, that randomness needs to be decreasing as you run the algorithm for a longer fixed amount of time, and that answer is converging towards the truth. Okay, so here's an example. Very trivial. Bless you. And this might be Yvonne's point. So a lot of people use Monte Carlo to estimate expectations. And so if I had an example like this, and I didn't know what the properties of the model were, let's say x is normally distributed with mean mu and variance sigma squared, and I didn't know what the expectation was. I didn't understand these parameters. I didn't know what the shape looked like in my head, and I can't do math. And I wanted to know, what's this? We know the answer, it's mu. But if I didn't know and I wanted to invoke Monte Carlo, I could approximate the answer. And this would be this. Xi's divided by n, where the xi's themselves are going to be coming from this normal distribution. Mu sigma squared. So I'm going to sample the xi's and sum them up. That's what this notation is. And then I'm going to divide by n. And if n gets bigger, then this thing converges to this. That's the central limit theorem. So that's really the law of large numbers really kicking in. But this sort of plain vanilla Monte Carlo is controlled by the central limit theorem. So we use this to estimate expectations all the time. And the question is how big is n need to be? These are the number of samples. before this is really close to that. And you can use the central limit theorem to analyze that. Because again, we're just doing averaging. So I'm going to show you a Monte Carlo strategy for just drawing samples from this posterior predictive distribution. And then we can use those samples to estimate anything you want, maybe the expectation or variance, which is some sort of an expectation, so on and so forth. You're not limited to just expectations, but certainly that's where all this stuff came from in the first place. So here's my Monte Carlo strategy. What I'm going to do first is I'm going to sample mu, and I'll put an index on this. I'll call it I. It's going to come from the posterior distribution. This is context specific to our example, where we're sampling from our posterior distribution. Which posterior is this? This is going to be a normal, x bar, sigma squared over n, right here. So that's my posterior in the example that we were just doing. Then I'm going to take my predicted draw. How am I going to get this? I'm going to sample from my sampling distribution. I'll call that f x tilde, given mu, but not any old mu. I'm going to plug in mu I, the one I just drew. So I'm going to collect that. And then I'm going to repeat this process over and over and over again.
Can I just ask really quick here? I thought the points of you couldn't compute this integral, so you don't have a posterior distribution.
I do have a posterior distribution. I didn't need to compute an integral to find it either.
Well, this is.
So it's the posterior on mu. What I would like to do is I'd like to sample from the posterior predictive. So let's just write down what that is. So we want to sample our posterior predictive distribution. That's our posterior predictive. I'll call it post-pred. And we know that that thing right there is equal to this. F x tilde, given mu, pi mu, given x. To do this integral in the first place, we needed that. I know what it is. Think about what this is, this integral. All I'm doing, really, when I see this integral, I do see a process. I see that I'm sampling out of that, I'm plugging it in here, and then drawing x tilde. And I do that over and over and over again. I really do just see that whole process. I'm averaging this thing over that. How do we do that? We draw from that, we plug it in, and we draw from that. What am I really getting? What I've just gotten is the joint draw. So this produces the joint. X tilde I and mu I. This is what we're going to get out of this. And I'll say I goes from 1 to however many times you want to do this.
I'm sorry, so what is the step after 2?
Stop repeat. So this is going to be a
Oh, okay.
for loop, and I'm just going to repeat this thing.
With just a new draw, I think. So you
Yeah.
don't your step 2 does not influence step 1, right? Each time it's the same. Okay.
That's how I jointly sample from parameters.
So
Check this out.
when does this converges? When do you?
We will talk about it in a second. Let's figure out what we're doing, but the answer is always the same. When it stops changing.
Yeah.
And you'll measure the change. And you'll measure which thing you want to track to see when it stops changing.
That's actually my question. So what are you keeping track of?
How about we understand the problem first, and then we'll answer the when do we stop? Figure out how to start first. So all good questions, but let me also just change this real quick. I'll say I goes from 1 to cap t for time, and I'm going to change this to time. T, we've already used n in our problem. There were n samples in here. That's what it is. So let me just be consistent in my notation. And so I've got a whole bunch of these samples. So this is just a collection of these pairs. That's what I'm getting. All I'm doing is I'm sampling from mu, plugging it in here, sampling from x tilde. That's the joint. That's what a joint distribution is. And so I could take any model. It's a very important point. Very simple, but important, very powerful. I could have a joint model. And I could sample, so let's just say my joint model is f, y, and z. These are dummy variables. They don't mean anything. And this distribution is just some weird distribution. Okay? I don't have anything particular in mind. I could try to grab, so this is a two-dimensional sort of thing, so I probably need to do this in two space. This might have weird margins over here. There's some mass over here. Some y, and z. I can't draw what that looks like in two space right here. So use your imagination and impute it. I can try to reach into this two-dimensional thing and grab points out of this space with heights proportional to the density. That's the goal. And I have to operate in this two-dimensional space to do it. Maybe I don't want to do that. I can write down this model as this. F, y, given z, times the margin on z. That's exactly the same thing. So how do I get this margin right here? I integrate over y. How do I get this conditional? I integrate over the margin on z from the joint. And so what I can do is I can sample this, plug it into here, and then sample y. So I can sample a zi from the margin. And then I can take that, I can plug it into here, and then I can sample a y. And I've just got a joint. It ends up doing the exact same thing. So that's what conditional probabilities and margins are all about, how we use them to form joints. That's what we're doing right here. So I'm sampling from mu, plugging it into its conditional distribution, conditioning on it, and then sampling the future point. So if I repeat this process over and over again, I will construct a two-dimensional representation of the histogram that looks like that picture I was trying to draw. That's what's going to happen right here. What do I do with this thing, is the question. All I want to get rid of the mu's. So how to get rid of the mu's? I've got this joint pairing between the x tilde and the mu, and all I want to be able to sample from is the x tilde, given all of our previous data. I don't want something joint with mu.
So I average it again?
So maybe I average it again. So I've got to store all these things, and then I average over mu's. What do I do with them? Anybody else? This is why I love Monte Carlo. The answer couldn't be easier. If I had a joint pair and I wanted margins, so imagine this. This is just a simple question. Back to probability 101. Let's imagine I drew a whole bunch of these numbers, y's and z's. And so I have y1, z1. I did this a whole bunch of times. Yt, zt. I have all these joint draws, but I don't want the joint. I want just the margin on y. How do I get a histogram representation on the margin on y?
Just take one.
Just take y. You can throw these away. So it's still distributed the way it is under y. It's got that joint structure. If I don't choose to look at the other jointly paired thing, then I have the margin. That's what it is. So that's why I love sampling, is you just kind of do whatever you want to do with it. It's kind of the most obvious, intuitive thing. If I want to know about some stochastic behavior out in the world, I can go out and measure it. I don't need to know what it's influenced by. If I wanted to understand pi x tilde cap x. And so in our example, turned out this was normal, and I probably wouldn't invoke this strategy because I already know everything I need to know about normals and I want to be exact. But if I cranked up t very, very, very large, I would get answers that were approximately close to what I could compute analytically. So these things end up looking like some sort of a histogram. up plotting those. And that histogram might look like the truth. So this is pi x tilde given x. And these bars right here are the histogram representation of this. If t is very, very big, this histogram will look just as refined as this curve. Or at least infinitely close to that. So long as you have an infinite amount of time to run it. And so Christina asked, how long do you run this thing for? Basically, you want to run it until it's a good approximation to the curve. And that answer can change depending on which distributions we're working with. So if the distribution is nice and normal, we probably don't need a lot of samples. I'd probably say go ahead, and if you used a couple hundred samples, it would probably be really great. But if the distribution we were trying to sample from was really bumpy, and it had a lot of bimodal structure, we'd need a lot more samples to estimate that wiggly structure. So it's a function of how complex your distribution is. And so what do you normally do? You normally track a couple things. If I were talking about a normal distribution, what might I want to check to see convergence? Probably the expectation and the variance. I would agree there are other moments, and we probably want those to converge as well. But usually we're focused in on those things. So I would say make sure whatever it is you want to report has converged. So if I wanted the posterior expectation, x tilde, given the past, how would I use these samples to approximate this? Exactly the thing I told you before. Yeah, just take the average. I goes from 1 to cap t, 1 over cap t, x tilde I. Now converge. What if I wanted the variance?
Use either 1 over n or 1 over n minus 1.
And then I construct a Bayesian 95% interval. It turns out that that Bayesian 95% interval should cover 95% of the time. Now I haven't proven that to you, but it kind of seems sensible if that's true, and we could do that math. And so I use that approach to validate all of my sampling schemes to make sure they're sampling from the right thing. And so I'm using a frequentist strategy to gauge my Bayesian machinery. So yeah, I think that you can use these things in lots of different blends and flavors. If you can repeat the process, being a frequentist isn't a bad idea. Then
So do we still have a 1 over t in front of the squared term instead of inside?
this 1 over t is in front of both of them.
Yeah, but there was a 1 over t squared previously.
I know, I didn't mean to write it.
Well, I mean.
Oh, I see what you're saying.
Yeah.
Got it. Yeah, I didn't fix it at all. I just made it even worse. Let's get rid of those braces. Difficult thing to think about. So this is over t, right there. So that's x tilde bar squared. The other thing is the second element. Thank you.
So how would the Monte Carlo procedure change for the non-IID case? Like the
So it wouldn't, in the sense that if I could sample from my posterior, it's just these two steps. Here's the thing that might happen in more complex models. You might not know how to sample from this. And so I'm assuming you know how to sample from both those models. You know how to reach in and pull out a value with relativity proportional to the height of the density. I'm assuming you know how to do that. And so in more complicated models, maybe in non-IID cases, not every single one, because sometimes you can perfect sample from those, I might have to invoke an approximate algorithm that approximately samples from these, but the sampling gets better and better the longer I run it. And so the sampling scheme converges. So there's no weight for these samples right here that we're getting for them to be distributed properly, if you know how to sample from both those distributions. You may have heard of Markov chain Monte Carlo. This is a class of algorithms that people use to approximately sample from everything. And that sampling gets better and better the longer you run it. We'll talk about that later in the class. And so that's what I'm always doing. Is I'm figuring out how long do I need to run this thing before I think it's converged. Similar to Christina's question. And then I invoke this frequentist paradigm for doing it. It's totally reasonable to do. We'll get back around to it and I'll show you how to do that blend later in class. Okay, so Monte Carlo's your friend. Let me just ask one more question before moving on. How would I do this? Say I wanted something really crazy. Say I wanted to estimate this. Expectation of some weird transformation. I'll say e to the x tilde sine x tilde arctan, say inverse tan log x tilde. How do I do this? I just made up a function. And I was trying to make it so that you wouldn't have a good answer on how you do this. Dan, how good are your integration skills?
Not good,
So let's
to be
not-
honest.
Mathematicians never integrate anymore, right? Only if they're teaching calculus. Tessa, you ready for it? I would, like, I'd try to write something down that you probably couldn't do.
Use metropolis, right?
And so I don't even need to do that. I want this expectation. These x tildes, I don't need metropolis. It's an MCMC algorithm. I can perfectly sample from everything, so I don't need an approximate sampler. I can sample the x tildes. So all I need to do to approximate this, if I can sample from my posterior predictive distribution, this is just going to be x e to the x tilde I sine x tilde I times inverse tan log x tilde I, absolute value. Hopefully I made a function that doesn't blow up to infinity. So all I do is I just compute this expectation again. Just plug it all in. Let me ask you a question. Don't I need a Jacobian? So isn't this a lot like when we do transformation of variables? That is what this is. It's the transform. What is this creature's distribution? I have no idea. If I wanted to approximate it, what I could do is I could plug all my xi's, x tilde i's into that thing and build a histogram on it. And it would be distributed, however it's distributed, just by transforming, and I just plug it straight into that equation. Don't I need a Jacobian? Don't I need derivatives to do this? I'm working in a continuous space. I'm working with these really complex things. Who thinks I need a derivative? You don't. Why?
Because you're just sampling from it and then plugging in the numbers. So it's not like a distribution anymore. You just have a function and then you're plugging for it.
Right. It's not like that. It is exactly that. But I guess it doesn't answer the question, why don't I need a derivative, though?
You
It's a
need a
simple answer.
derivative whenever it's a PDF or a CDF. and
Isn't
you're
this a
plugging-
continuum, though? It's not. I've got a very discrete, a very refined discrete representation of a continuum. So when you do discrete transforms, you just plug everything straight in and you don't need the stretch factor, the derivative, the Jacobian. And so I operate like I'm operating with discrete things because they are discrete. So it's my best discrete representation. And so you can just do this. I love Monte Carlo. If I can sample from a distribution, I can answer any question you want. So about that distribution, so long as I've got enough storage and a little bit of time. Nowadays, it's a pretty simple business. So we all have computers that can do this, and the amount of samples that you can store is pretty incredible. We'll talk about MCMC later when you don't know how to do this sampling. Let's switch gears and see if we understand from the last couple weeks everything we've learned. So I'm going to change the examples and do everything again. I want to change the example to xi's are coming from a Poisson distribution. which usually have, well, they have one parameter. Again, everything's IID. And here, we'll start with n samples. And then I need some priors if I want to do a Bayesian analysis. So somebody help me out. What does this look like? Probability of x given lambda. Just write down lambda x over x factorial e to the minus lambda. And so x's are going to be an element of the counting numbers. I guess it can be 0 as well. So 0, 1, 2, 3, so on and so forth. And lambda has to be positive. So these are counting numbers. So Poissons are distributions on counts. So this is just totally different sort of thing. Lambda, however, is continuous. So if we're going to do Bayesian inference, we're going to learn lambda, which is going to be a continuous distribution given discrete counts. So in the normal distribution, everything was just normal all the way through. Here, the posterior distribution and the sampling distribution have totally different interpretations because they don't even live in the same spaces. So does anybody know what this means in French? Fish. It means fish. So if you've ever been to a gourmet restaurant, you see this term all the time. So Poisson's actually a person. That's nothing to do with fish, and maybe in some lineage of his name, that's where it comes from. So I heard somebody give an articulate explanation that this model was created because people were out there counting fish with it first.
No.
I don't think this is true. So this is a person, so famous mathematicians, probabilist, who's understanding all these connections between probability models. And so do you know where this model comes from? A couple different conceptions of this model. So I usually consider the Poisson as the foundational counting model, and then I can change some stuff with it. I will tell you real quickly, expectation of x. I'll be specific given lambda. Does anybody know what this is? It's lambda. And the variance of x given lambda. Does anybody know what this is? It's also lambda. So this is kind of interesting, that the expectation and the variance in a Poisson model are exactly the same. Does that make sense to you? Say you're counting something. The higher numbers you count, and let's say you count with error, would you be making bigger errors as you counted higher? So imagine this problem. Imagine I gave you some big buckets, let's say little buckets, with about 10 or so apples in them, and I asked you to count all the little apples in all the buckets. I asked you to count all those up. You'd probably do a pretty good job. However, if I ended up making the buckets with thousands of apples in them, you know, and you're counting through it, and you're like me, you'd make mistakes and forget where your number was, what did I just count? And you'd start to make errors. More errors as the count got bigger. So this is kind of the idea right here. And so it turns out counting models, if they're going to be part of the exponential family or be derived from it, the variance of counting models can never be smaller than the expectation. And so if you ever see that, if you ever see counting data and you notice that the variance is really small compared to your expectation, it's not coming from something that can be derived from the exponential family. That is a really weird property. I'm going to tell you where it comes from. It probably comes from a mixture representation of data. So if you ended up having a whole bunch of modes of counting data, then you might be thinking that the variance was much, much larger because you'd be talking about the variance between those modes. And so what you really want to do is bring down the variance for each one of those little systems. And so we'll talk a little bit more about that later, but it turns out in counting models, if you want to make the variance higher, you can do it. I'll tell you how to do that next time. But if you want to make the variance lower than the expectation, you're going to need something like a mixture representation. So also, interestingly, let's imagine x was binomially distributed. Binomials have two parameters, n and p. if we ended up taking n to infinity while simultaneously taking p down to 0, such that the rate limit n goes to infinity, p goes to 0, np, this thing has to go to a constant. So as long as this limit exists, so if you ended up doing this, we usually call this constant lambda right here. That will have a Poisson representation. So this limit of the binomial turns out to be Poisson. And so one interpretation of Poissons is that they're rare event models. So they can be used to model rare events, things that you count out there, but n is very, very big. And the probability of that thing happening is very, very small. So that might be one way to think about this distribution right here. Let's just answer an easy question. What's the conjugate prior for lambda?
Gamma.
Let's do our Bayesian analysis. We kind of know why we might like these models. Maybe we don't like the constraint that the mean is the variance. I'll tell you how to fix that later. So, let's back up. What's the likelihood? I usually don't try to answer the question about conjugacy until I write down the likelihood. Likelihood looks like this. So, lambda xi over xi factorial e to the minus lambda. So, it's just going to look like this. Lambda to the sum of the xi's. I have this nasty product down here. I will tell you, if you ever see this on a computer, there's two things that should scare you instantly.
The product.
This product of factorials, these numbers can explode really fast. And even the e right there might give you some pause. So when you see these functions, get nervous if you're going to actually use them and implement them. We'll talk about it in a little bit, but what's the conjugate prior? Did you guys say it? My ears are clogged today.
Yeah.
It's gamma. Yeah, looks like a gamma. If I multiply by a gamma, slides right through. And so, looks just like the same kernel form that we had for the precision. So the answer is gamma. What's the posterior? It's gamma. We just need to recognize what the parameters are. So our posterior distribution is proportional to the likelihood. And notice this. This just contains the data. It doesn't have my parameters locked in there. And so my likelihood is also just this thing. So I don't even have to worry about that. That's a great advantage. So I condition on that thing, I don't even have to compute it.
Is it a constant of proportionality in your case? That's why you.
That's why I'm writing proportional. I'm not even going to work on this normalizing constant. Turns out you can't write it down. I can write gamma function, but I haven't really written it down analytically. So this just looks like this. So my prior has the form lambda alpha to the minus 1, e to the minus lambda beta. Then I just multiply in my likelihood. This is going to look like lambda sum of the xi's, e to the minus and lambda. I just combine terms. Lambda can be alpha plus sum of the xi's, minus 1. Don't absorb your minus 1. You're going to use it to recognize your updated parameter there. E to the minus lambda beta plus n. This thing right here is a gamma. alpha plus some of the xi's, n plus beta. The expectation of this model, I can just look at real quickly and see if it makes any sense. This is going to be alpha plus some of the xi's over n beta, n plus beta. And so it looks like a penalized form of the expectation of the sample mean. We could work out the variance as well. We would just square out the denominator. And so pretty easy thing to do. We'll come back next time, ask ourselves, does this make sense? It makes pretty good sense. We'll ask ourselves what alpha and beta should be. We might already have choices for those. Those are pretty good. So it turns out I can derive those mathematically and give you the reference priors, and they are that gamma 0, 0 again. So fascinating example. Last question before you depart. What's the posterior predictive distribution? Hard question. We'll be working and chiseling away at that on Monday. It's not a Poisson. Thanks, you guys. That's it for now. I've also put a homework up online, so if you want to have at it, I've given you 2 weeks to complete it. We'll be doing review sessions next week.